In this video, we are going to be discussing question 12.11. So we are supposed to draw the resonance structures of the following molecules. So before we start that, when we have benzene involved, that is C6H5, then you need to remember that the substituent group, we need to decide if it's electron releasing or electron withdrawing. So if it is electron releasing, you have a negative charge which will move around the benzene ring, whereas if it's electron withdrawing, you'll have a positive charge going around in the benzene ring. So the first one is C6H5OH. So C6H5OH is a benzene ring with an OH group, right? So OH is it electron releasing or electron withdrawing in nature? OH is actually electron releasing. So oxygen itself will have two lone pairs of electrons, so one of it will go in, form a double bond, and this bond breaks. So you get a positive charge on the O actually, and here you will have a negative charge. Now this will move in here, this will move there. For a detailed explanation about resonance structures and what resonance effect is, do check out the video about the same. This is just a basic understanding as to how to draw the resonance structures, and I'm assuming that you already have that. So this negative charge will again shift in and the bond breaks. The reason bond breaks is to maintain the tetravalency of carbon. So here you will have a bond, double bond. Here you will have a negative charge. So I'll get another double bond, and that's why because the number of bonds with oxygen is 3, and so it gets a positive charge. Okay, this negative charge moves in here, this goes back, and so we have the lone pair of electrons back at OH. And so these are the resonance structures of phenol. OH is an electron releasing group, so the negative charge is getting delocalized. The next one is C6H5NO2. I think we had already discussed this in one of the videos. So NO2 is electron withdrawing in nature. So here you have a nitrogen double bonded to oxygen, single bond to another oxygen atom. So because nitrogen has more than 3 bonds, it has a positive charge, and 1, 2, 3, 4, 5, 6, 7, 8. Oxygen will have a negative charge, and that oxygen has the lone pair of electrons. So this is the structure of nitrobenzene. So what happens is this bond shifts up there, and basically this double bond will break. So nitrogen double bond, single bond to oxygen. Okay, and since this moved, this will get a positive charge. Now, unlike the previous case, in this case we will not be moving around the positive charge, but the arrows will indicate the movement of electrons, and that's always the case. So this arrow indicates that the bond has moved up. Okay. Okay, so here you have the double bond, so obviously you'll have a positive charge on the para position. Nitrogen has to have a positive charge because the number of bonds it has is still 4. Now oxygen, both the oxygen atoms have a negative charge, and you have a bond here. Now this bond will shift downwards. Here double bond, a positive charge. Okay, that looks really bad. Sorry. Then you have a double bond here with the nitrogen, the oxygen atoms. Oh, positive charge. I keep forgetting. Do not forget the positive charge. It's very important. And the negative charge, that's equally important as well. And then the last structure is basically going to be, because negative charge is basically going to shift back, or it can be the other way around as well. Like, so this negative charge can move here and form a double bond between nitrogen and oxygen, and this double bond going to shift here. Remember, resonance structures, you always have to put double-headed arrows in between the structures, not on the structure itself, but between them. Okay, no space, I'm just going to write it here. Double bonded O, so only 4 lone pairs of electrons. Single bonded, so we'll have 6 lone pairs. The negative charge. So NO2 is electron withdrawing, and so these are the resonance structures of nitrobenzene. The next one, we have a double bond and an aldehyde in the straight chain. So let's just write the structure first. So CH3 has a single bond, CH, double bond, CH, single bond, CH, double bonded to oxygen. So it's an aldehyde. So oxygen is more electronegative than carbon, so it will tend to pull the electron, the double bonded electron, towards itself. So the resonance structures can be, this bond shifts there to the oxygen, CH, double bond, CH, 1 2 3 4, 1 2 3 4. Okay, CH, single bond O with a negative charge, and obviously CH will get a positive charge. Now there is a double bond over here, right? So this will shift over here, right? And that leads to the formation of another resonance structure. And more are the number of resonance structures, more is the stability. And here in this carbon, 1 2 3 and 4, it has 4 bonds, so its tetravalency is, basically followed, but then this carbon has only 3 bonds, and since the electrons move to the other one, it gets a positive charge. The next one is benzaldehyde. So let's first draw the structure. Like NO2 nitrate group attached to the benzene ring, benzaldehyde will also be is also electron withdrawing in nature. So what happens is, this double bond moves over here, and this double bond shifts to the oxygen. So the oxygen gets a negative charge, and the benzene itself will get a positive charge. This benzyl carbon, or the carbon of the benzene ring, will get a positive charge. So similar to how we moved the electrons, and we didn't put the arrows for the positive, we don't do this, right? We don't show the movement of the positive charge. Instead, we show the movement of the electrons. Doing that is actually wrong. We only denote the movement of electrons. So the double bond is shifted here, so the positive charge comes here, and you have you have a double bond here. So CH, double bond, single bond O. Now again, this bond will shift downwards, and so the next structure will be double bond CH, single bond O minus. Okay, now this bond has shifted here, so obviously this carbon is going to get a positive charge. Next, this will shift down, and then this will come back to the benzene ring. So the double bonds and the COH. So like NO2, even the aldehyde group is actually an electron withdrawing group. The next one is a benzyl cation. So you have a CH2 which is having a positive charge. Now, the CH2 is electron withdrawing in nature because it itself has a positive charge. So, it will pull the electrons towards itself. So, this bond breaks and basically shifts to here, and the positive charge is going to get basically for the benzene ring. So, here you have a double bond CH2. I think we had discussed the stability of the benzyl carbocation, and we discussed that. We also spoken about resonance. We had spoken about resonance as the reason for its stability. So for a detailed understanding about how to draw these structures, do check that also out. So this bond breaks and moves to this side, and then you have a positive charge here, here, and here you have two double bonds and the double bond to CH2. And then obviously it shifts back down. So CH2. The last one is CH3CH, CH2 with a positive charge. So let's just write that down. CH3, CH, double bond, CH, single bond, CH2 with a positive charge. So similar to what we did in the case where we had an aldehyde, we will just shift the double bond here, and this carbon is going to get a positive charge. So CH3, CH with a positive charge because it has only 3 bonds and the double bond has shifted to the other 2 carbons. This is the other resonance structure. In this case, we had another aldehyde group, so we had the third resonance structure because of the oxygen, CHO group present over there. So with that, we're done with 12.11. In the next video, we'll be continuing with the textbook exercises.